Okay, so let us start by basically going through the what you're supposed to read for this lecture. This lecture is mostly based on chapter 2 in the book. I have not gone through everything in the book. I expect you guys to go through everything in the book because, well, if the only reason that I'm giving these lectures is for you guys to re- basically re-listen to whatever you read in the book, then I'm a useless guy. This chapter is our basis. There is some material that is not in the book, not much, but there are things that these are things that I thought would be useful for you guys to understand the material in the book also. I have skipped a couple of code examples. There are code examples throughout this book in general. I will probably go through some of them. I'll skip some of them. That does not mean that you guys can skip what I skipped. It just means that I found it better use of our time to do something different. Uh, I do just for if you guys want to know what books I use like around 4 or 5 books to basically get the material in the best shape I can, hopefully making it better. You're not. I do not ask you to go through more than the book that we have specified. I use the other books just as basically to add things that would explain things better or add a couple of nice information that you guys should know. I believe should know out of this course. So we'll go through a bit of what we went through last week. Well, it wasn't last week; it's actually 2 days ago. So let's start by saying what happens when a program runs. And basically, you as a user, you do not want to go through how does the memory gets managed, what parts of memory am I assigned to. Even as a programmer, I mean, you do not do that in most high-level programming languages. You do a bit of that in C, but not in Python, for example, or in Java, which I believe many of you have been working with, or hopefully have started working with. So the primary mechanisms that an operating system use to divide resources among different users is to give them a virtual space, sort of a virtual resource, that a virtual set of resources. These virtual resources are the resources that gets assigned to your program, and that gives you the feel that you have the whole computer all by yourself. So the operating system takes a resource, be it the processor, the memory, the disk, and transforms it into a more general, powerful, and easy to use virtual resource for both the programmer and the user. This is an example of how the operating system virtualizes CPU. Again, this code is in the book. It's actually available even for download as is. You can just download it from the book website. So you have it. You don't need to copy it. And I expect you guys to try every single piece of code that we go through, unless I basically tell you that you shouldn't. So, virtualizing the CPU. This is a very simple program that basically takes input from the user arguments and sleeps for 1 second, prints the argument to the screen, sleeps for another second, prints the argument to the screen, and goes on in an infinite loop. Okay, so we can go through the code very quickly. You have the includes, basically libraries that you're going to use. Some of them are actually libraries that have been built by the book authors. Some of them are the standard C libraries, basically. And you start the program. This is your main. You double check that the user has provided some input for you for the program to print. Basically, if the user has not provided any input, also known as arguments, then you would just print an error message. Otherwise, you store the argument. You go on an infinite loop. Spin is basically your sleep function, and then you print the line spin print, spin, and go on forever. So if you run a single instance of this program, you first have to compile it, of course, and then you run it, you give it an input, and then simple, it prints basically whatever input that you have given to it. But now suppose that you actually run multiple instances of this same program. So you run it with inputs as A, B, C, and D. Right now, you have 4 processes starting, and this program basically, these lines basically tell you the process IDs of each process. And I hope you know what AND is in Linux, and basically runs it as a background process. And you run basically all these instances of the same program using 4 different inputs as background processes. And then the programs do what they are supposed to do, which is basically print whatever input you have. But you see something interesting here. You basically have an ABDC, ABDC, ACBD, and this order can change. And the change in the order with which you see the printing shows you how the operating system actually virtualizes your resources. Because what's happening is that every single instance of your program gets some time on the processor, gets scheduled for some time on the processor, and depending on the order on which the scheduler puts them, you will get the output. Okay? And basically, this is a huge part of what we're going to study in this course, which is basically the scheduler. How do you schedule things on the computer? Another example of such programs are programs with concurrency. By programs with concurrency, we mean a program that has multiple threads, multiple things going on in the same program at the same time. I'm not really going to go through the code that is provided in the book. I want you guys to go through it. I hope you'll get some of it, but we are going to be covering that code in great details over the coming couple of lectures, basically. So I prefer not to go through the code until I basically go through the actual theory behind that code. And in general, there are some programs that basically do multiple things at the same time. So suppose, for example, a web server, like an Apache web server that runs almost all of the internet. For example, if you go on Wikipedia or something, you provide a URL, and that URL basically translates to some resources that the Apache web server serves to you. So if you look at an application like this, you do not have a single server per user. You have multiple users, and you have that server serving all users. One way to program such applications which serve multiple users is to have threads. Basically, whenever a user comes in and tries to fetch something from the web server, you will have thread serving that user. We'll go through the details and the definitions of threads and so on to a great detail in the course also, and how to build concurrent and correct programs. So this is a very hard problem actually, and the whole paradigm of parallel computing actually you can say that it basically tries to build correct concurrent programs. This is another example where you're actually virtualizing storage, and storage is an interesting thing because, as you know, if you're running on a real computer, not on a laptop, well, a laptop is a real computer, but I mean like the kind of computer where the large ones basically. So if you're running on a computer, not a laptop, that doesn't have batteries, if you pull the plug, you lose everything. And many of us might have even lost data when they were writing, for example, in a Word file or in making a presentation, forgot to save it, and bam, you lost everything. So you want persistent storage or persistent I/O in your system. Basically, you want to be able to store whatever data that you write in a Word file to your hard disk, so that when there is a crash, there is a power failure, you do not lose data. So this is a simple program that basically writes to disk. And writing to disk is not a simple task. It's actually a very complicated task. This program opens a file. It uses the open system call to create a new file. this is also something that we're going to cover in this course. System calls, it writes 13 bytes to that file that it just opened. This file now is in system memory. So now you write it, save your Word file using the write system call, and you basically assert is basically to check if things went correctly, and then you close the file pointer. So if you look at this at this program basically, sorry, the file descriptor. If you look at this program, basically, this program writes to disk. It might seem that it's a straightforward forward task, but what is actually happening is that your user application is using a programming language API. So if you're using, for example, Python, then it's called open again, and then you can write using the print statement. You can write using a write call also in Python, and so on. So you have a programming language API. I'm a Python guy, so I might give lots of examples in Python. So you have a programming language API that then contacts the system calls, which is basically the interface between the operating system and whatever lies on top of that. And you have these system calls dealing with the file system, which is a huge part of the operating system, which then talks to the device drivers, which are basically the controllers that actually control your actual hardware, and then that writes the file to the persistent storage, which is either your hard drive or your solid state drive or your USB stick or whatever it is. So we'll cover this also to a great detail in this course. We come to the point where we ask ourselves, what is the kernel? The kernel is basically what we're going to study in this course. The kernel is the innermost portion of the operating system. We're not really going to go through the interface between programming language APIs and system calls. We're not really going to go through device drivers because these are not the inner core. We're basically going to go through the inner core of the system. And the inner core is called the kernel. Of course, the kernel can include the device drivers, it can include the system APIs, but we're going to go through the very central parts of the kernel. It manages your hardware, it manages your software, and it distributes system resources. So if you look at this, this is basically your applications on top. You have system libraries, basically Python, Java, C++, whatever you use. Then you have a kernel interface, which are basically the system calls. We're going to cover this. You have the file system, the virtual memory system, the TCP/IP networking, and the scheduling. And then you have hardware-specific and device drivers at the bottom of the kernel, which is basically also sometimes called the hardware abstraction layer. In this course, we're going to go through system calls, file system, virtual memory, scheduling. We're not really going to go through the TCP/IP networking stack in the kernel. This is something that you learn about more in networking courses, although you might not learn about how it is implemented in the kernel, but you can easily go from whatever theory you learn to looking at the kernel code. There are a few main kernel components. The first one is the interrupt handlers. And this is basically something to serve interrupt requests. An interrupt is something that happens due to some event. Let me give you an example of an event. When you actually type on your keyboard, when you click on your mouse, when you basically type on any of your keys, you cause an interrupt in the system. You basically tell the system that some event has happened now. The operating system handles these non-real time, these non-reoccurring events using interrupts. So right now I've been sitting, both hands here, for maybe a minute or two without clicking anything. But once I click to basically change the slide, there will be an interrupt in my operating system. So this is part of your operating system. There's the scheduler, which we actually talked a bit about when we were looking at the CPU example, which shares processor time among multiple processes. There's the memory management system, and there's the system services such as networking and inter-process communication, and also to some extent the file system. So let us take again a step back and ask ourselves what happens when you basically click on the start button on your computer. You basically have the BIOS, which is the basic input output system that executes something that's called the master boot record. The BIOS is basically uh, it's a pre-programmed memory in your computer, doesn't change, also called read-only memory (ROM), that is on your computer, and that basically when you click, when you press on the start button, the BIOS basically knows where something that's called the master boot record is, and that is basically the first part that starts your kernel. It basically points to a place in your hard disk that starts something called grub, or Grand Unified Bootloader. It's the basically, okay, here I am. I got power. Where do I go now to find my operating system? I don't know. So I go to the master boot record, which is some part in all hard disks. That basically is like, I mean, you'll always have it when you install your operating system. You actually change the master boot record. You go to the master boot record, which basically tells you it's basically some part in your hard disk that points you to the grub. You load the grub into your memory, and if you have been using dual boot machines, for example, you can have multiple grubs. You can basically choose between, well, Linux, Windows. Am I starting in Linux? Am I starting in Windows? You pick one of them, and then you load the kernel into the memory. The grub basically points you to the part in the hard to that part in the hard disk that has the rest of your operating system, the rest of your kernel. You start your kernel, you start your init. Init basically starts all the different services that you would need in your system, like network, like like networking, like Bluetooth, whatever you have your system configured with. And then basically your program is running, or sorry, your operating system is up and running. Of course, you can have things more than the kernel starting at the beginning, and that basically you have these are the run level programs. Okay, so you have here physical memory, and you have the disk. You load things from the disk, you put it in the physical memory, and so on and so forth. Let us look at some very basic architecture. This is basically your motherboard. Most of them would look like that, maybe different colors, maybe they look nicer, maybe they look much uglier. It depends. You have some input output connectors over here. Sorry. You have an audio chip, which is basically your sound controller. You have your processor. This is basically your chipset, which is your actual processor, your Intel or AMD processor. And you have some processor support. I mean, you need cooling, you need different things like for your processor. You have here your motherboard power supply connector, which basically connects to your power system. You have the RAM, which is your memory. Okay. You have things such as connectors to your disk drive and floppy drive if that thing exists. And you have your BIOS, which we were talking about. So your BIOS basically points you to the master boot record that we were talking about over here, which basically is somewhere on disk. We don't have the disk over here. It's connected through one of these connectors, and then you basically go through BIOS master boot record, which is on disk, basically tells you, well, you need to load this grub, which goes to the RAM, to the memory, and then you basically choose Linux versus Windows if you have that if you have that installed. If not, then you will just from the grub basically start fetching parts of the different parts of the operating system that you need from the hard disk, which is connected through this. The processor, I mean, these are all things that that are very basic for you to know how the operating system actually runs. The processor is a very simple device that basically has a program counter, okay, which points to a line in the memory that you fetch, you run, and you basically go and fetch a new program count, a new program line. So what you're doing here is that you have a program counter that points to somewhere in the memory. It increases typically by 4 or 8 or 16 or 64. I mean, that's I don't care about that right now, but basically something that goes through memory line by line to execute something, to run something. And this is where you go over your program, basically. And you might branch. So, for example, you might have if else statements. So, if this thing happens, well, you might want to change the program counter completely because you're going to jump through code and go to another line of code. And there's else statement that might make you make another jump. Okay? So, normal operation, you go sequential. If you have branches, then you basically jump.